Hello students, welcome to the lecture on statistical decision theory, and after the lecture we will be able to learn the following objectives. Explain the meaning and the scope of statistical decision theory, explain elements of statistics decision framework, describe decision under uncertainty, discuss the expected monetary, explain the expected opportunity loss, explain expected value of perfect information, describe the uses of incremental analysis. Let's start with a brief introduction to statistical decision theory. Decision theory is an interdisciplinary area of learning that concerns mathematicians, statisticians, economists, philosophers, managers, politicians, psychologists, and anyone else interested in the analysis of decisions and their consequences. Decision theory, as the name would imply, is concerned with the process of making decisions. The extension to statistical decision theory includes decision making in the presence of statistical knowledge which provides some information where there is uncertainty. Decision making is the process of sufficiently reducing uncertainty and doubt about alternatives to allow a reasonable choice to be made from among them. Let's now take a look on meaning and the scope of statistical decision theory. A decision problem involves a set delta of states that represents possible situations, affairs, etc., and a set X of potential consequences of decisions. An act is considered as a mapping from the state space to the consequence set. It is a natural behavior for human beings to make a decision based on earlier experience that could often be modeled as statistics due to the uncertainty. Statistical decision theory is the mathematical framework to make decisions in the presence of statistical knowledge. Let us understand the elements of statistics decision framework. Given a statistical model, the information that we want to extract from data can be in various formats depending on our purpose. We may have three common problems: estimation to deliver a good guess of an important parameter, testing to know whether the data supports certain specialness, ranking to give an order based on samples. Statistical decision theory is essential to modern digital communication theory, which the transmitter essentially sends binary information represented by one of the two possible waveforms to the receiver through the channel. Let's talk about decision under uncertainty. The phrase decision under uncertainty refers to the problem of taking decisions when we do not have a full knowledge neither of the situation nor of the consequences of the decisions, as well as when the consequences of decisions are non-deterministic. Paradoxes of uncertainty. The distinction between uncertainty and probability has centered on two paradoxes. One of them is the paradox of ideal evidence. Ellsberg concluded that the degree of uncertainty, or conversely the reliability of probability estimates, must be taken into account in decision analysis. Risk analysis: such is the task of the risk assessor to use whatever information is available to obtain a number between 0 and 1 for a risk estimate with as much precision as is possible, together with an estimate of the imprecision. Measures of incompletely known probabilities. These rules that have been proposed for decision-making uncertainty, partial probability information, all make use of some quantitative expression of partial probability information. A binary measure divides the probability values into two groups: possible and impossible values. In many cases, the set of possible probability values will form a single interval. Multi-valued measures generally take the form of a function that assigns a numerical value to each probability value between 0 and 1. This value represents the degree of reliability or the plausibility of each particular probability value. Decision criteria for uncertainty. Maxi-min expected utility. According to the Maxi-min EU expected utility rule, we should choose the alternative such that it is lowest possible EU, that is, the lowest according to any possible probability distribution is as high as possible, maximize the minimal EU. Reliability weighted expected utility. If a multi-value decision measure is available, it is possible to calculate the weighted average of probabilities, giving to each probability the weight assigned by its degree of reliability. Ellsberg index. The use of an optimism-pessimism index to combine maxi-min expected utility with what is essentially reliability weighted expected utility. Modified MMEU. Decision rule that makes use of a measure rho of epistemic reliability over the set of probabilities and certain minimum level rho 0 of epistemic reliability is chosen. Levi's lexicographical test. It is assumed that we have a permissible set of probability distributions and a permissible set of utility functions. Let's now have a look on expected monetary. Expected monetary value is a value that is based on probability that factors in all possible monetary outcomes of a given situation. The ideal situation in making a decision would be to know the outcome before the decision is made, especially when it comes to ones involving money. If you could somehow determine precisely what would happen as a result of choosing each option in a decision, making business decisions would be easy. Calculated expected monetary value, EMV. After conducting a qualitative risk analysis, we will have a list of risks with a priority and urgency assigned. By using expected monetary value, we can quantify each risk to determine whether qualitative analysis is backed by numbers. To calculate the expected monetary value in project risk management, we need to, step 1, assign a probability of occurrence for the risk. Step 2, assign monetary value of the impact of the risk when it occurs. Step 3, multiply step 1 and step 2. Expected opportunity loss. Here we will discuss about expected opportunity loss. An opportunity loss is the payoff difference between the best possible outcome under SJ and the actual outcome resulting from choosing AI given that SJ occurs. For the better understanding, take a look on the screen. The EOL can also be depicted with a decision tree, of course. Note that for a given probability distribution, the expected payoffs EMV and EOL for every action alternative AI always add up to a constant. For better understanding, take a look at the screen. Let's now take a look on expected value of perfect information. The effective management of uncertainty is one of the most fundamental problems in decision making. While uncertainty can arise from a plethora of sources and assume a multitude of forms, in this paper we focus on parametric uncertainty within the framework of quantitative medical decision-making models. We examine and critique 3 measures of decision sensitivity that have been utilized in the medical decision-making literature based upon the threshold proximity, probability of a threshold crossing, and entropy. In contrast, EVPI considers not only the probability of decision change but also takes into account the payoff differential resulting from such a change. EVPI equals to expected value under certainty, maximum EMV. Let's talk about uses of incremental analysis. Incremental analysis is basically a worksheet technique in which the relevant costs of one alternative are listed in one column and the relevant costs of another alternative are listed in an adjacent column. Under appropriate circumstances, incremental analysis is a tool for evaluating decision alternatives such as keep or replace, make or buy, sell now or process further, lease space or continue operations, continue or discontinue product line, accept or reject special offer, change credit terms, open new territory, buy or lease incremental analysis model. Buy or lease. Open new territory, buy or lease. Incremental analysis model. Incremental analysis is a flexible tool. Data may compute and present for the life of a decision alternative on a per period basis such as a month or year. This procedure would require the relevant cost items to be divided either by the number of years or the number of months in the life of the assets under consideration. The basic incremental analysis model used in this program may be mathematically summarized as shown on your screen. Let us understand the correlation and regression. The concept of correlation is a statistical tool which studies the relationship between two variables, and correlation analysis involves various methods and techniques that is used for studying and measuring the extent of the relationship between the two variables. Two variables are said to be in correlation if the change in one of the variables results in a change in the other variable. Correlation. A model consists of some factual relationships, some equations, some identities, and some constraints. Once a model like this is formulated, the next issue is to examine how this model works in the real-world situation. Many complex econometric models consisting of hundreds of functions, equations, identities, and constraints have been constructed and estimated for different economies of the world, including India, by using empirical data. The correlation coefficient lies between +1 and -1.
Hello everyone and welcome to this brief overview of correlation. So what is correlation? Correlation is a relationship between variables. By looking at a correlation, we can get an idea of how strong this relationship is and what type of relationship exists between our variables, so more about the direction. One feature of a correlation is, of course, its direction. By looking at whether or not a correlation has a positive or negative sign, we can tell what is happening between the variables. Also, we can take a look at a graph of a correlation and quickly see what direction our correlation is in. For example, a positive correlation occurs when both variables are increasing or decreasing at the same time. Our data set will fall in an upward sloping direction when we have a positive correlation. So if we have a data set that has points that look like what I'm putting on here now, we can see that if we drew a line through this data, going in an upward sloping direction. What this tells us is that as our variable x increases, our variable y is also increasing. Okay. Now, a negative correlation is what exists when our variables are going in opposite directions, meaning that as one variable increases, the other decreases. This gives us a negative correlation. So in this case, our data set will fall in a downward sloping direction. So if we have a data set that looks like this, and we draw the line that best fits this data set, we can see that it is going down. Okay. Now, what this means is that as our values for x increase, as we move along the x-axis, our values for y are decreasing. They're going down. So we can see here that our variables are going in opposite direction. As one is increasing, in this case our x value, then y is decreasing. Now, if our data set doesn't seem to follow either one of these predictable patterns, then it may be described as having no correlation. No correlation means there is no discernible pattern that can be detected between the variables, meaning that no relationship exists. This can happen in two different cases. One, the first one I'll present here, is where our data set appears to be scattered, where it has no real pattern. So let's say, for example, we had a data set that looks like this. Now, if we drew a line through this, like we did for the positive and negative correlation, you could see we would really have a straight line. This would be the best fit here. If we ever see this type of data set, or we can draw a straight horizontal line, then that means that there's no real relationship between x and y. Another way that we could possibly have a no correlation is if we have something that is curvilinear, which means that maybe our data set looks like this. It seems to curve around. So if we drew a line, it would appear to be this way. And we could also do a data set that would go in the opposite direction as well. And what this means is that it's not a reliable linear relationship. We can see here that when x is really low, so in this case right here, or when it's really high, y is low. And we can see that drawing a best fit line through our data set here does not lead to a sloping line or signifying a direction. A positive correlation, again, is signified by a positive sign, and both of our variables are going in the same direction. This can be from 0 to +1. A negative correlation, again, means that our correlation is from 0 to -1 or has a negative sign, and our variables are going in opposite directions. No correlation will be close to 0, so it will have no sign, and it means there is no discernible relationship between the variables. Another feature of a correlation is its strength. The closer the number is to 1, regardless of the sign or the direction, whether it's positive or negative or has a positive or negative sign, the stronger the correlation is. Though we would have to look up the critical R, or correlation coefficient, which is affected by the sample size, to determine whether or not the correlation is large enough to be significant, we can get a basic idea of the strength by simply look at the correlation coefficient itself. We can see here that an R equal to plus or minus 0.8 or higher is typically referred to as a strong correlation. An R equal to plus or minus 0.5 to 0.8 is considered a medium correlation, while R of equal to plus or minus 0.4 or lower is usually referred to as a weak correlation. Now we can have this for any of the types of correlations, positive or negative, that we were talking about before. For example, a strong positive correlation would fit a straight line, or would be very close to that straight line. So, for example, very similar to what I had listed up at the top of the screen, if we had a data set like this, where our best fit line would go right through the middle, of course that's supposed to be a straight line, then that would be a very strong positive correlation. The closer those dots or the points in our data set are to that line, the stronger the relationship. And the stronger our correlation, the greater that number will be to 1. Now we can see this especially in, let's say, a weak positive correlation. Now again, it's positive, so our data set will still go in maybe an upward sloping direction. You can see here that our points are spread out more. They're not packed greatly around the line that we have here, or the best fitting line. So this would represent a weaker correlation. Overall, remember that correlations tell us about a relationship between variables, how strong that relationship is, and in what direction those variables are going. However, we cannot infer causality or say that one variable is impacting or affecting the other.
Regression. The term regression literally means a backward movement. Regression analysis can be described as a study of the dependence of one variable on another or more variables. In other words, we can use it for examining the relationship that may exist among certain variables. A major purpose of regression analysis is to predict the value of one variable given the value of another or more variables.
There are 3 basic steps in a linear regression. First, we look at the scatter plot. Second, we perform the regression analysis, which generates estimates of population parameters. Third, we interpret that analysis. Why do we start by looking at the scatter plot? First, because there may be a relationship between our variables, but the relationship may be nonlinear. Here's an example of a nonlinear relationship. If we would look at the scatter plot, we would see that. It would save us the time of going straight to a linear regression, and we could instead use other nonlinear techniques. Second, a quick look at the scatter plot may just tell us there really is no relationship, as in this data that I randomly generated. Doesn't look like a relationship, so I'm not going to try a linear regression. Now, on the other hand, here's actual data that I pulled. On the y-axis, hedge fund returns from the HFRI hedge fund index, regressed against, or in this case, just plotted against, returns from the Russell 3000, a good proxy for the overall market. And a quick look at the scatter plot, at least to me, says this looks like a linear relationship and therefore worthy of a linear regression. And so the linear regression, in this case, draws a line through the data, and that line represents the best fit. There's a purple line here because this plays a role as well, and this is just the average of the y values. But the red line is the regression, and it is expressed by the linear regression formula here, given by y equals alpha plus beta multiplied by x plus epsilon in this case, which is the error term. So the error term plays an important role. So that's the linear regression. It's a best fit line. How did that line get generated? Well, typically by ordinary least squared methods. And so if we take one of these observations, like this observation right here, and look at the distance from that observation to the regression line. If we take that distance and square it, and then do the same for this next observation and for each of these observations, and so we can call that the distance the error between the actual observation and the y as predicted by the linear regression. We can square those and sum those. That gets us a big number. This line attempts to minimize that number. Ordinary least squared attempts to minimize the sum of the squared differences between the actual observation and the predicted y on the line. So this is the linear regression formula. Pretty simple. I show it here three ways because sometimes we see it with different notation and we don't want to be thrown by the notation. These all mean the same thing. In some cases the intercept may be Roman A or Greek alpha or even B sub 0. But in all cases, if I just take this first one here, we have y, the dependent variable, is a function of or equal to the intercept. That's the y-intercept. Where does that line hit the y-intercept? Plus the slope, that's b or sometimes beta, multiplied by x, the independent variable. So we can say y is dependent, x is independent, y is a function of x, or the way I like to think about it, y depends on x. And finally, don't forget the error term. The error term reminds us that this line, it will never be a perfect fit. There is error or dispersion between the actual observations and the line. Realistic data will never fit on the line tightly. So error captures that dispersion and reminds us that this is just a prediction of y. This formula, intercept plus slope multiplied by x, is just a prediction of y. The actual y is going to be some error off of that. So, to summarize, x is the independent, y is the dependent, and the error term is the residual that reminds us x tries to explain y, but cannot fully explain y. So that's a quick introduction to the linear regression equation. This is David Harper of the Bionic Turtle. Thanks very much.
Now in the end, let us summarize what we have learned in this lecture. Decision is one of the most common human intellectual behaviors, and mathematicians have spent over 300 years to analytically tackle this issue by establishing decision theory. The classical approach to decision theory facilitates the use of sample information in making inferences about the unknown quantities. The logical approach has contributed to the understanding of the decision-making process. Statistical decision theory is essential to modern digital communication theory, which the transmitter essentially sends binary information represented by one of the two possible waveforms to the receiver through the channel. The distinction between uncertainty and probability has centered on two paradoxes. One of them is the paradox of ideal evidence.